Perfect. All right, I'll just introduce things here and then hand it over to Maxwell and Jesse. So welcome, Python user group. We're kind of dormant for the summer, taking some time off, but hoping to get things back going now that kind of the school year, I guess, has started, even though probably none of us are in school. Tonight, we've got two remote hosts, Maxwell Strikeout Doolin and Jesse Victors. I'll let them introduce themselves further, but they're both security engineers, or in Jesse's case, a senior security engineer. Maxwell's presented at DEF CON, among other things, and they're going to be talking about Python meets radio, wireless radio signals and stuff. I'll let them talk about it more. So Spokane Python User Group is part of a bigger Spokane Tech Groups, which is just a few different Spokane technology groups. I think I mentioned that to people here in person. We've got the .NET Users Group, which typically meets on the first Tuesday of the month, I think, and the DevOps Group and the Python Group. We're sponsored by Intelitech, which is the building that we're in right now for people here in person, based out of Spokane. If any of you are looking for software development jobs, we're always hiring. Especially for senior people right now, I think. .NET User Group, I think they just met a couple weeks ago. They don't have the next one scheduled yet. They might be moving to quarterly is what I heard instead of monthly. So there might not be anything scheduled for another month or so. Python, we are, so I'll say this maybe more than once, but at least once, we're actively looking for speakers. That's kind of how Maxwell and Jesse, Maxwell saw that I was just searching frantically for people to speak because I was sick of kind of being the only one hosting. And I think people were sick of listening to me talk every month. And he was kind enough to offer up them to present. So thank you, both of you guys. I will say that you do not need nearly as much experience with Python or as you think you might to talk about something. It doesn't even necessarily need to be Python related. Adjacent technologies, some other programming language. They are talking about wireless signals. So, I mean, I think we've got an animator, a 3D designer here. If you even somehow talk about Python for 30 seconds, you are more than welcome to talk about your little niche.
Right on.
And then the DevOps group, again, I think they're moving to quarterly, so I'm not sure when their next meetup is. We've had some great presentations about Terraform, Kubernetes, Azure stuff, that kind of thing. Follow Intelitech on the social medias. This recording will be posted to the Intelitech YouTube channel probably tomorrow. I'll add the link to the event on meetup.com. We also have our website, SpokanePython.com, which I'll add the link to both places. Jump the gun here, but meet today's speakers, Maxwell Strikeout Doolin and Jesse Victors. Thank you both for being here, and I will turn it over to you guys.
Cool, thanks, Joseph. Jesse, if you want to pull up the slides and share those, that would be awesome. Major shout out to Joseph. The reason I am here is because I noticed he was trying to pay people to come to talk. And I said, I don't like that. You are running something for the people and you're trying to pay people. That you shouldn't be doing that out of your own pocket. So now I am here and we refuse to take the money. We want this to be a good thing for the community. You pulling up the screen, Jesse?
Apologies, Jesse, you should be able to present. When I restarted the meeting, it untoggled that.
All right. Can everybody see them now? Cool.
Cool.
Now we got them rolling. I'll let Maxwell take it away for a bit.
Sick. So this talk is titled Python Meets Radio. I kind of like Boy Meets World, and I wanted like a short, snippy title, so that seemed good. The picture in the bottom is actually something our friend at work wrote, and it's like the opening cast pictures from Boy Meets World, but instead like their faces are blurred out and they all have radios in their hands. I think it's really funny. Look at the next slide. Cool. So Jesse and I are both hackers at Security Innovation. We do a lot of weird stuff, like anything that's non-web, non-mobile. That's what we tend to do. Like I do a lot of hardware stuff, a lot of reverse engineering, a lot of binary exploitation. I run a class on heap exploitation just because it's fun to teach. Jesse is way down the rabbit hole on this radio stuff. Like, you should see his house with all the antennas that are just absolutely everywhere. Like, he's had to like be careful with HOAs and stuff to make sure he isn't violating the rules. It's quite comical to see how much he's into it. But I've also learned a lot from Jesse, so it's been pretty good. Recently, some of the projects we've done were mostly wireless. So I figured out how to open my parents' garage door using SDR. We pwned a scoreboard and recently published a blog post on that. Jesse's really into the amateur radio stuff, and pretty much everything I do at work that I need to program is in Python. So, of course, everything we did in this is Python, so it seemed like a good thing to talk about. Did I miss anything there, Jesse?
You got it.
Oh, no, actually, one more thing. Yeah, we work at Security Innovation, and we hack lots of cool stuff. If you're looking to hack cool stuff, then come join us and hack all the things. If you need people to hack stuff, then please call us because work is nice. All right, next slide. Had to give the quick plug.
Of course.
So the outline of this talk is going to be a very high-level overview on the basics of radio signals. Originally, we made this talk. We had way too much stuff in there, but we tried to limit it to the amount of stuff that allows you to understand the stuff later in the presentation. But this rabbit hole is endlessly deep, and I don't fully understand most of it. Jesse probably doesn't either, but you can get pretty far with knowing bits or little bits and pieces depending on what you're doing.
Sorry.
Yeah, you're good. We're going to talk about software-defined radio, what that is, how awesome it is, and then we're going to talk about how to interact with it via GNU Radio, and that is a common software development kit for interacting with software-defined radios. After that, we're going to talk about two different case studies that we've from projects we have done ourselves and how we actually use GNU Radio to accomplish our goals.
Right. Yeah, go ahead, Maxwell. Sorry.
Before we continue, anybody have any questions on anything I just said? All right, cool. Crickets in the background. All right, cool. Next slide. Cool. So the basic thing is, what is a radio wave? Radio wave is electromagnetic wave, just like things like light, infrared, except we can't see the radio waves. Practically how this works is a transmitter is sending an alternate current, which is going to leave this piece of metal. Then somewhere down the line, after this wave travels at the speed of light, it will interact with some other piece of metal. And this other piece of metal is what we commonly refer to as an antenna. If this is, even though it's going to be extremely low power, if you know what you're looking for, you can definitely find it. Next slide. So one thing that always confused me was that wave I just showed you is just a sine wave. It's very consistent. So how do you actually add data to this? And adding information to this is a process we call modulation. There are three main types of modulation that I think are worth talking about as a high-level overview, but there are weird subcategories, or you can combine them. People have fun with it for sure. The first one is amplitude, or this is like how loud something is. So if I'm talking loudly or I'm talking quietly, then that could change or that could be some sort of information being sent. So me talking loudly could be a 1, and me talking quietly could be a 0. On the same vein, you have frequency, where if I talk in a very low voice, it could be a 0. But if I talk in a very high voice, it could be a 1. I know, it's good voice. So those are the two easier ways to describe. Unfortunately, phase isn't nearly as easy. I can't do phase with my voice, even though I have tried to figure out a way. If you think about back in the day doing, going to math class, and you're dealing with not signals, but like a sine wave, you always talk about things being like at 90 degrees, 180, 270, and all the way back to the beginning at 360. And phase shifting or phase modulation is the act of changing that degree in order to encode information. Even though that seems crazy because of how fast these waves are moving, it is a detectable thing, and a lot of things use it. I think I was doing this, right?
Yep.
Yeah, okay. Do you have any question on the extremely high level overview that we gave on the waves and the modulation?
Nope, we're good.
Cool. Either you guys have no idea what's going on, or I explain it so well that you don't need to ask questions. All right. So now where does software-defined radios come into this? If you go to the next slide, I think I have a pretty cool analogy for this. So back in the day, when Pong, which is the image on the left, that game was actually built in hardware. There were physical circuits that were made in order to program this game. So you couldn't just pop in a new CD and start playing it. And that was cool for having a game at the time, but you had to have very specific hardware just to play this one game. So the newer generation of game consoles are very generic. So you have the Xbox One here, and it has a lot of the rendering stuff abstracted away. The game, or the person developing the game, will build it, or will call those interfaces, which then display stuff on the screen. The cool thing about this is the developer is in full control of what is displayed on that screen. It's completely generic. You can display whatever you want, you can do whatever you want, and that's the really cool thing about the game console. If you go to the next screen, this is the other thing that makes software-defined radios so cool. If you take a look at the original radios, it could only do amplitude modulation within a very specific range of frequencies. And all that's really cool. You could listen to the baseball game at Yankee, in the Bronx back in the day. You really missed out on a lot of the potential capabilities this had. You could only listen to AM radio, and that was it. Now, we're talking about the generic side, just like the Xbox we talked about a minute ago. Like before with the Xbox having interfaces to display stuff on the screen, the software-defined radio, or in this case, I have a picture of the HackRF, is that same generic interface. You can get very low-level information back from the HackRF, and then you can interpret it however you want in software. This could be AM radio, this could be FM radio, this could be airplanes overhead, this could be your Key-Fob. This is literally anything. Because it's such a low level, you can then interpret it however you please. And that's what makes software-defined radio so powerful, is you can write applications for anything. But what can you actually do with it? And it turns out that wireless signals are all around us, absolutely everywhere, all the time. One example that I think are really cool, next slide, please, is you can track airplanes. And I believe that somebody in the crowd was talking about tracking trains, which is probably a pretty similar thing. All airplanes are constantly sending out information via the automatic dependent surveillance broadcast system. And that picture is a tad bit small, but if you look on the right side, there's a graph, or not a graph, like a table, and that table tells you information about what flight number it is, where it's traveling, coordinates, and then there's a picture that somebody actually somebody designed a nice user interface that parses that information and then displays where this plane is going and where it's currently located, which I think is really awesome. And this was done because of software-defined radios. Somebody was able to take the raw information that comes from a software-defined radio and parse it in such a way that they could write this piece of software. I think that's really amazing. Next slide, please. Now, there are many, many other things. Like pager traffic is still really common, believe it or not. When Jesse and I sniff on stuff in Seattle, we see pagers from Amazon and a lot of hospitals, garage doors. Like there's a lot of different things in the air that are actually pretty interesting to parse. I remember during the riots that were in Seattle, you could actually listen in on the police frequencies, even though you're not really supposed to be able to. So they kind of knew where police officers and stuff were going at the time. Next slide. So how do we actually go about doing this? That airplane application seems really cool, but how do you go about getting the information from that software-defined radio and finding something meaningful out of it? Or in the reverse, how do you send something? Like what if you wanted to host your own AM radio station via software-defined radio? And that's what the bulk of this presentation is meant to be about, is using the GNU Radio tool chain in order to listen and transmit signals. Next slide. So the first thing that I think is really good to know are waterfall graphs. This recording right here is this in cubic SDR or
It is.
GQRX?
I think it's cubic.
Okay, cool. There's a lot of different tools that do the same functionality, but this is a waterfall, aka spectrogram. And if you look closely, you can see it says 88.5. And if that sounds familiar, it's a radio station. The bright yellow indicates how powerful the signal is. So if it's yellow and red, it's going to be a powerful signal. Where it's blue, it's going to be very low power. And at the top of this graph, you can also see there's a hump. That axis is, or the x-axis is going to be frequency, and the y-axis is going to be amplitude. So you can definitely see the signals and how powerful they are. I think it's pretty rad. And this is a good way to find out where a signal is actually located at. Next slide, please. This is a waterfall of some digital communication. We're going to be talking later about Jesse decoding some his key-fob. There was a vulnerability discovered in Honda cars a couple years ago, and Jesse was working on replicating that research. Okay, another person. Cool. But you can see that there's very bright colors in that graph, and you can see the frequency is around 313 megahertz as well. Next slide, please. If you noticed in the previous slide, it appears to be two signals going at the same time. Jesse, could you move your mouse cursor around the two humps? No, around the two humps there. Yeah. So you can see that there's like two distinct humps there. And if you remember from the modulation schemes we were talking about, there were a few different ways to do it. And one of them was frequency. Because there are those two distinct humps that are right next to each other, we can pretty easily tell this is going to be frequency modulation. We are quickly moving between two frequencies, or the pitch of my voice, in order to encode the information. And on the right side, this is actually using frequency modulation in the tool. So it's trying to decode it for us. And you can see that there's a longer stretch of high frequencies, slightly smaller stretch of low frequencies, and then it oscillates between high and low. And this indicates that we have some sort of binary data in the form of frequency shift keying that we could decode, where the high frequency is going to be a 1, the low frequency is going to be a 0. Next slide, please.
Yeah.
So, questions. Does anybody have any anybody have any questions or thoughts on any of that stuff? If that didn't make sense, please ask, because we want to make sure that the rest of the presentation makes sense. We have quite a bit of time.
Is the name in that tool Cubic SDR? Is that what you were saying earlier?
Yes, Cubic SDR is at the top of the slide here. It's a free program you can get for Linux and Windows, I think. I think it's for Linux.
I use GQRX for what it's worth on my MacBook, and it works pretty well. But there's probably 8 tools that do the same thing. They all have different perks.
Yeah, all the waterfalls kind of end up looking the same. It's all about the utilities built around it that are kind of handy. The next thing we want to talk about is what I would call is breaking out the really big guns, and this is GNU Radio. Yeah, exactly. So this is a pretty useful tool, but it can get pretty complicated. But thankfully, it's all about Python, as I'll shortly explain. So what is GNU Radio? It is a framework for digital signal processing. So if you have a software-defined radio and you're looking to extract a signal or send a signal, this is going to be one of your go-to tools. And in fact, you're going to find it in a lot of different communities, a lot of different blog posts. A lot of people turn to this tool for more advanced uses. So even if you haven't heard of it before, we're going to give some pretty good examples and kind of walk you through how this works and how it relates to the Python. So here is a very simple example. I'm looking right here at GNU Radio Companion, which is basically an add-on. It's a GUI for GNU Radio. So you can basically see that we have some basic blocks we have here. We start with this vector source block. We have a throttle block and then a GUI. So like Legos, they kind of link together and you build these flow graphs, technically called like the directed acyclic graphs, but basically they're just flowing from point A to point B through the different blocks. So basically here, the vector source picks up this variable called digital sequence, which has 1 0, 1 0 0 1 1 0. It's just an array of characters. These are treated as floats, and then they're sent through. They're repeated and sent through the throttle block, which speeds them out at 16,000 per second, and then puts them on the screen at this GUI and makes this little graph. So now you can see the 1 0, 1 1 0, this alternating and repeating pattern that is set up here. So this is a very, very simplified example, but we'll kind of show you how this works. Under the hood, it just compiles to Python. So this is it. This is basically the Python for this. The GUI makes it a lot easier to construct, to build, but basically, as you can see on line 42, it's just connecting the blocks together in Python. So you can actually use GNU Radio entirely in Python if you want. In fact, a lot of people do that for more advanced purposes, or if you need custom processing and things like this. But at the root of it, you basically just start up by setting up these variables, defining the terms that you need. Then you basically load these blocks from the GNU Radio library, and then you connect them together with literally self.connect, and then you basically pass in the blocks that you want to connect. And that in the GUI, those are kind of the arrows that you end up seeing. But since I'm a visual person, as flow graphs become more complicated, it's handy to have a GUI build it and then just kind of generate the Python for you, even if you don't want to be there. But I've seen people go both ways. So you can find a lot of GNU Radio examples that are entirely in Python or entirely in GNU Radio Companion, but they're really compatible with each other.
One other thing on GRC or GNU Radio Companion that's really cool is, like Jesse said, there are a lot of pre-built blocks for it. Yeah. So Jesse's using a source and a sink, and then something in the middle, but maybe want to modulate the data in some way. And there's going to be an amplitude modulator, a frequency modulator, and then all of the other shenanigans you need to do digital signal processing correctly. A lot of them are very low level, but it's cool to have all these tools in your tool belt to have at your disposal to do stuff.
And I do also want to point that I'm far from an expert in GNU Radio. It has a very steep learning curve, and when we first started about a year ago, it was nigh near incomprehensible. But it's quite a useful tool once you kind of understand how to assemble the blocks that are precompiled and useful utilities into something larger. And with that, I'm going to turn it over to Maxwell for the next section here.
So anybody have any questions on the GNU Radio stuff? We're going to be talking about actually using it in a little bit. I just wanted to give you guys a quick sec. Ask questions first.
Yeah, we're good.
All right, cool. So if you go to the next slide, Jesse.
Yeah.
I think I substituted the pictures. I did, not disclosing bad information. Good job, Max.
Yeah.
So one of our main use cases, because we're security engineers, is hacking stuff. How can we use this here? And we decided we wanted to use 2 case studies in order to demonstrate the use cases of GNU Radio. And they're not just some arbitrary thing that's thrown on the website. These are things we actually did that we're actually going to be explaining, all of the highs and lows of it. As we mentioned on the previous slide, we recently hacked a scoreboard. And if you go to the next slide.
Yep.
There's starts to be more information there. And we had absolutely no idea how this worked. We didn't know what modulation scheme it used. We didn't know the baud rate. We didn't know anything about it. But the end goal was to always build our own controller for the scoreboard. Next slide. And I'm going to spare you the details on a lot of this stuff because it was just a painstaking amount of reverse engineering. But at the end of this reverse engineering, we knew exactly how the packet worked. We didn't know every one of the little itsy bitsy details. We explained some of the cool Pythonic beauty stuff we're able to do to get it working. But this is what the packet looked like. And this is a packet like you'd see in TCP. It has some sort of information at the beginning, and then it has information in the middle of, or that's way too generic. Come on, Max. The very beginning of the packet has a preamble, and this was in order to tell the receiver, hey, wake up, come on. The sync word was to sync the two clocks between the devices together. So we have a transmitter and a receiver, and the transmitter and receiver need to make sure they have the clocks working at almost the exact same time. Because how do you tell the difference between a 1 and a 0? It's by the clock. After that, there was a length byte. This determined how long the packet was. After that was an encrypted payload. For some reason, these people were using AES encryption in order to on part of the wireless packet. And after that, there was a CRC, which stands for cyclic redundancy check. And this is in order to see if the packet's been corrupted or not. If one bit was flipped somehow in the encrypted payload, then we know that the CRC would be different when it actually got received. Therefore, it would just ignore the packet. On top of all that is, can you go back for a sec, Jesse? Sorry, you're good. Is data whitening. And data whitening sat over the top of the length, the encrypted payload, and the CRC. So what is data whitening? Now we're good. Data whitening, if you look at the bottom image, you can see that the transmission data is being XORed with some sort of random data. This random data was being generated with a linear feedback shift register, also known as an LFSR. And if you look at this image I made in PowerPoint, or this GIF, which seems impossible, but PowerPoint is the greatest thing ever. We start with, we're taking 2 bits, and we're going to, from the registers, and we're going to XOR them together. Those bits are then outputted, go back into the register and are shifted over. The output of our XOR operation goes into the very end of it, and then the output is just the bit that was in register 0. But there is a problem here. How do we, or if this is all zeros, then it will repeat for 0 forever, because 0 XOR 0 will always give us 0. So the problem we ran into is the documentation did not include an initialization value for the LFSR. Go to the next slide. So my coworker Max and I came up with a really weird solution. We know both the real size and the whitened size of the packet, and the length byte was the first byte that was data whitened, but it wasn't encrypted. So our thought was, let's brute force every possible state for the LFSR and see if we get the right output. What you mean by this is we would plug in the small packet and large packet real size, and we would test different initialization values until we got the exact right whitened value. And eventually we found it. And the script didn't have to run for very long. It was just the idea. Let's go to the next slide. It ended up being all ones. It seems completely logical it would be all ones, but we didn't know that going in. We just had to try them all. Yeah, if you go to the next slide, we run into the second part of this we had to use Python for. Because the traffic was encrypted, of course, we had to decrypt it ourselves. Although these are decryption screenshots, this is how I first discovered it. We had to use some hardware hacking black magic to find the key, and the key ended up being 1 2 3 4 5 6 7 8 1 2 3 4 5 6 7 8, which is a very secure key. And no, it's not. Please don't use that key. It was really bad. So yeah, luckily for us, Python is super easy to use, and this is all the code I had to write for the decryption step, and it was about the same size for the encryption as well. If you go to the next slide, there's one more final piece to the puzzle for the packet that we had to put in, and this was the CRC check. So again, this is to make sure a mistake was not made in the packet or not. If you go to the next slide, we couldn't get the algorithm to work. The documentation included the algorithm that was being used for this, but it wasn't working. And there's a black magic tool called CRC reverse engineer. If you Google that, you'll find it. I learned about this on a podcast, and you can plug in a bunch of different values. So you can plug in the entire packet with the CRC at the end of it, and it will find whatever your initialization, or it will find all the parameters for it. And it popped out the right polynomial for the CRC, but it also found the proper initialization value. And it turned out that this RF module was using a non-standard initialization value. If you go to the next slide, it's really easy to implement this in Python. I love this meme. If you can't see it, it says, "This is plagiarism. You can't just do import essay." And that's a lot of Python things. Is a lot of stuff just pre-written for you, and you write a couple lines of code and it works. If you go to the next slide, my CRC code is very small. It's literally like I import a library, I put in the right parameters, and then I run the CRC and it's done. So at the very end of this, we have all this code implemented in Python. We have the CRC, the data whitening, the packet format. We got everything programmed in Python, but we don't have the bits in the air. And that's where GNU Radio comes into play, where we want to take that information that we can now generate the proper bytes for, throw it in the air so the scoreboard will actually interpret it and update the scoreboard. Does anybody have any questions? Sorry, Jesse.
No.
On any of the stuff we just talked about? It's not really related to GNU Radio, but we figured it's fun to see like all the stuff that was required and how you can hook into GNU Radio later.
Yeah, so question here. You hear me?
Yeah.
Yeah, okay. To do with the data whitening. So that's literally just to make sure that you're not sending the same symbol over and over again.
Yeah.
The radio
Yes.
symbol, so that you don't lose track of the clock.
Yeah. So Jesse, if I go back to that slide, I think this actually will help.
Yeah. Here?
Yeah.
Yeah.
So, with how the clock sync or the sync word is used to make sure the clocks are synced up correctly. However, if there's too many consecutive of one bit in a row, then the clock gets out of rhythm. It's hard for it to know perfectly where it's at. I believe if it's like 6% off, it fixes itself, but anything more than that becomes bad. And I think the RF module, if it was like more than 16 of the same symbol consecutively, then it would lose that, or it would the clock would get desynced. So by randomizing the data being sent, it would that clocks, or by randomizing the data, you don't have that clock synchronization problem.
Yeah, you make it less likely that you send a whole string of just zeros or just ones, and you always have some. You're not always, but you make it more likely that there's some sort of state transition.
Yeah, exactly.
That you can reset your clock from. Yeah.
The state transition is the important note. Thanks for clarifying and calling that out.
Yeah.
I appreciate it.
Yeah, no problem.
Because you know how it's being whitened and how it's being encrypted, could you put the inverse of the whitening in the payload so that you could essentially generate all zeros? Because it would be the XOR of the whatever all zeros encrypted is.
Yeah, exactly.
Essentially do a reauth attack to drown out the regular transmitter.
Oh, hold up. I maybe I misinterpreted you a couple of different ways. Are you saying like transmit your own thing on top of this signal, or are you talking about like trying to? Yeah.
To make the receiver think that the sender's dead, because it's the whitened encrypted payload is all zeros.
I mean, you're still receiving data because it's not going to see all zeros when it's going to get to the RF module, and it's like, oh, I'm having data coming in, even if and then it unwhitens it or de-whitens it. Does that make sense?
But because the whitening is a exclusive OR, right?
Right.
So you could send the opposite of the data that whitens to all zeros. And
Yeah, I mean,
lose the clock.
I see what you're. I think I see what you're saying. Yeah, we could. Yeah, this became complicated because of the number of layers to like the encrypted payload and the data whitening. I do want to point out that a lot of signals are also have data whitening. And there's also a popular method like using line code. But I think the trouble with the advantage of using data whitening is I don't think you have to double your baud rate or double the speed of the bits, which these were transmitting at 250,000 bits per second in just frequency shift keying, which is
Holy smokes.
which is so enormously fast that like most of our tools could not zoom in enough to see them. Like you couldn't actually figure this out. So this took us quite a while to like go. It was insanely fast, and so I think that's why they chose data whitening over like just regular methods. But I do want to point out that the same techniques apply because you need to have different bits in a row to make sure you don't lose track of. So you can always distinguish, one consecutive bits from each other.
Yeah.
And their max length was only 255, so that's not a lot of payload to mess with.
Yeah.
Sorry, Jesse. What was the baud rate?
250,000 baud of two level frequency shift keying.
Yeah. Okay. Yeah. I mean, that's fast for a little key-fob or something. But I just wanted to say to anybody involved here, if you're on Wi-Fi right now, then you're getting considerably higher number of bits per second on that.
Well, yeah, but that's when you get into like QAM and you get into like multiple different frequencies, and you're building this like big thing. But this was just one single stream, and it was like insane. So certainly there's other techniques to like pack more bits in there, which we were kind of skimming over. But I'm just letting you know that like this was crazy. So I think that's why they chose the data whitening.
I'm just pulling your leg. We're club buddies.
Yeah. No, I'm with you. You do this all the time in the Discord, so that's cool. Okay.
Do you want to? All right. So we were on to the GNU Radio side of the Scoreboard, and this is where Jesse just talks about all the cool stuff that I don't fully understand now.
Yeah. Again, this. So as Maxwell was saying earlier, at this point we had used Python to reverse engineer all of we've cracked the encryption with some hardware attacks. We'd figured out how to build the stuff, but we were at the thing where we had the binary that we needed on the computer, but how do we actually get it out of the air? And for that, we need a modem, not like a 1990s modem, but like our own software modem. And modem is just a demodulator and modulator. That's what it stands for. And for the modulator, we use GNU Radio. This turned out to be the flow graph that we used. After all of this reverse engineerings, we actually have to send it down. This is what we used. This looks a little complicated, and it really was. And we had to get some help in building it for the first time. But I can kind of show you how it works, and it's all Python under the hood. So at the very beginning of this flow graph, we kind of start with the bits. These are the bits that we set up for the scoreboard for our project. We needed to deliver to the actual display. So we start, we basically take the digital sequence variable and we feed it in as the source block, right? Then this gets into the next block, the repeater block. The repeater block has an interpolation block utility to it, where it's going to basically expand out each 1 or 0 to be each 1 is going to be 450 ones, each 0 is going to be 405 zeros. Like they're going to be expanded out because we're moving the samples through our flow graph faster than the 1s and 0s need to go to the scoreboard, and the two have to match up. So the throttle block. Go ahead.
We're trying our best to turn this back into a continuous signal versus like digital bits, and this is part of the process that allows us to do that.
Yeah, absolutely. So we basically are streaming out these samples that are the wave that we're going to be delivering at 5 million samples per second, which is about the speed that the HackRF1 can handle. And so to match the speed of the bits that we need to get to the scoreboard, that's where we use the interpolation to make sure our math matches up and all the ones and zeros are at the right units of time, essentially. Second thing, this is the real meat of the modulation part of it, okay? And the key is the voltage controlled oscillator, which is just a fancy, in hardware is kind of an interesting little hardware circuit, but in software, it basically operates the same way. So the VCO, the voltage controlled oscillator, if you send it a high number, it's going to go to a high frequency, like the E, really high pitched. And if it's a low number, it's going to go to a low frequency. So if you send ones and zeros, you're going to be shifting between the high and the low frequencies. That's going to give us the frequency shift keying. So the second step is a low pass filter. It's kind of removes some of the extra noise built from the mathematics, gives us a clean modulated signal where now the ones and zeros are jumping between these two different frequencies. In kind of the diagram here, you can kind of see what I'm talking about, where you're kind of building these higher frequency waves when it's a 1 and the lower frequency waves when it's a 0. And you're kind of building it along from this particular part of the flow graph. Finally, we do have to point out that the Hacker F1 and some other SDRs have a little power spike in this at the very center of wherever you tune it. This is just based on how the hardware works. Our solution to it was to send and receive slightly offset. So we use a mathematical method called the rotation. Technically, you're just rotating around the complex unit circle, but we don't really need to get into that. I do want to point it out because the next block that we have is the rotator, and it's called that because we're doing that mathematical operation. We're rotating backwards and shifting that frequency down to avoid that hardware issue. And finally, we deliver the results into the Osmocom sync, and that's the driver that actually gets into the Hacker F1. And on the right, you can see that the setup that we made. So then our wave that we have built in software with the ones and zeros that we built for the scoreboard are going down at USB. They're going into the software-defined radio, the Hacker F1. They're going into our amplifier and then to the custom Yagi antenna that we built. And then they're going to be delivering it, kind of directionally beaming it forward into the scoreboard. Now, in my mind, as a true hacker would, I pictured someone taking this little antenna and set up and hiding it in a tree or something and messing with the scoreboard like remotely, because that would be kind of sneaky and clever. But yeah, basically this is the hardware that we use to finally finish that pipelining all the way to deliver it, the attack. So the entire thing is Python. Here's basically that whole flow chart again, and it just turns into these sort of steps in GNU Radio. If you may remember from the simple example, we have the variables, blocks, and the connections. And then each of these components, each of these steps, like Maxwell said, they're pre-built. They're probably compiled in C. They're hooked into by the Python. So when you do these complex mathematical steps, it's not executing in Python. It's probably executing at native speeds, and it runs along very efficiently on your computer. So you got hardware optimizations, and it usually keeps up pretty well. But because it's Python, and all of the scoreboard processing was in Python, we can basically just hook the two together. So the entirety thing becomes one unit, and it's very easy to connect together. And for that, this is your slide, Maxwell.
Yeah. So like I talked about before, we abstracted this as much as we could. So we have the scoreboard, or we have the utils, so like the CRC, the AES, all that stuff in one file. And then we have the scoreboard data, which then calls all the utils. And this keeps the format of the packet to be exactly how it should be. Because within the actual scoreboard information, there's like the game clock, the shot clock, the score. We want to make sure all that stuff's formatted properly. And then finally, we have the packet. And this makes sure that we have the preamble, that things are whitened correctly. This does all of the shenanigans to make sure that when we actually give the information to GNU Radio to send off, it is correct. If you go to the next slide, the controller is what we use to edit the field. So we've abstracted this one layer up. we wrote a CLI that allows us to just edit the scoreboard data directly. So we can alter the shot clock or the game clock or add whatever sort of functionality we want on top of that. Next slide. The cool part to this, though, like Jesse mentioned, is we can just hook this in real fast. There's a variable in GNU Radio that we set up called digital sequence that Jesse showed before, and our controller literally just modifies that variable in GNU Radio, and that's it. So by having, we had the static digital sequence from before, and we simply just modify that one variable, and now we can change what gets sent wirelessly. And this is some example code that we wrote. This is the controller's set game clock function. Excuse me. You can see that we're the data packet.scoreboard.set game clock, and that is we're calling a function within Scoreboard to change the game clock directly. And then the Scoreboard modem is being called to update the digital sequence, which is hooking into GNU Radio, and it's taking the raw bits from our packet, and once it gets updated, it will then get sent. So I did want to show a quick demo. I think this is kind of fun. This is a video wrote up. If you want to let it roll, Jesse.
Yeah.
The image on the right is the CLI we wrote, and I'm editing stuff in real time. So you can see that I'm setting the team name to Duke and Gonzaga. So Gonzaga is playing Duke, but we all know who's going to win this one. It's going to be Gonzaga. And I'm setting the Gonzaga score to be 120, and I'm setting Duke's score to be 78, of course, because Gonzaga is better. And then we can let the game clock go on that as well. So that's a pretty obvious attack. If Jesse goes to the next slide.
What is it? We have arbitrary commands. Oh, yeah, arbitrary commands. We have the next one.
Yeah. So then the next one is the clock.
Oh, yeah, okay. Oh, here. Oh, sorry, it's not clicking. Hold on. Oh,
you're good.
Yeah, got it. Okay. All right.
So this is my personal favorite. This is the fast clock attack. So we were able to alter time because at the end of the day, it's just bits that are being sent in the air. And because it just periodically updates the scoreboard, we can update it at whatever speed we please. So the clock in the top left is an actual clock with real time. And we can see that we're ever so slightly speeding up the clock. And if you've played basketball before, you know that 3 seconds in a 30-second game or shot clock is a big deal. Or at the end of the game and you make the horn sound. Like once you have control of the scoreboard, you can actually influence the game. I believe is this the last stuff we have on the scoreboard, Jesse?
I believe so.
Okay.
Hold on. Here we go.
It
won't let me jump at the same time. Yeah. Yeah. Yeah.
Oh, I was gonna give a pitch. Jesse and I did write a series of blog posts about that entire thing. That was a pretty short snippet of actually creating the wireless signals, but finding the AES key was pretty interesting. Reversing engineering the signal was interesting. So if you're interested in that, Joseph will hopefully point to my blog where all those resources can be found.
As far as we know, it's the first time that anyone has ever conducted wireless attacks against the scoreboard. And so it looked like it was pretty interesting, and we submitted it to DEF CON and everything. So
did not get accepted.
We did not get accepted.
Something.
I'll
be okay.
Yeah, but yeah.
Did people have questions on that?
You're muted.
Yeah, go ahead, Joseph.
I was asking, so on the scoreboard that you attacked, there was separate commands for horn start and horn stop.
Yeah, there are. That's a different bits in the sequence that we reverse engineered and then delivered through GNU Radio through Python to the scoreboard.
That would be really annoying if your controller ran out of batteries after sending horn on. Or you suppressed.
Yeah.
Turn off.
Yeah. What's even funnier though about that attack is we accidentally learned this, but if you trigger the horn on off repeatedly, the receiver crashes. Which is really funny. When I mean repeatedly, I mean like
Faster than
20
you can
times a second or something.
faster than you can
Certainly
physically.
have the bandwidth to do that.
Yeah. Oh yeah. Yeah. Well, I think it leads to some very interesting attacks from like a cybersecurity perspective, where if you were continuously broadcasting your own signal of the scoreboard, but with the horn turned off, the moment that the real person like scored, and then the real refs like turn the horn on, you'd have two conflicting signals going on at the same time, and that would lead to the crash. But they wouldn't know what happened, because from their perspective, they just pushed the button and it crashed. So you could get away from like these very subtle conflicting attacks that are invisible, and it's really hard to detect. But I think that could be some interesting real world attacks if you wanted to be evil, so the next
I had a question real quick before you guys move on to the next.
Yeah.
Can you explain a little bit more about that type of antenna? Yeah, I don't remember what it was called. And I
Oh
wasn't
yeah.
familiar with it.
Oh boy.
Here we
Okay.
go.
Oh for goodness. Oh boy. Well, I'm sure. Yeah. I know it's not a Pringles can. So this is a Yagi antenna. It's not perfect. I basically made it. I went to Lowe's and I bought. You can probably recognize that I have like one of those like short pieces of like cylinders, or the square cylinders, whatever they are, prisms. And then some very thick copper wire that I got from those giant spools that they have on one of the shelves. And then I basically I used a calculator to very carefully cut them to specific sizes and put them and drill them into the right locations, so that the wave constructively interferes with itself and kind of concentrates its power going forward. I was not perfect at this. This is my first time building something like this, and I don't have a very like professional looking or very good match here. And I'm sure Adrian is. I mean, I didn't get the impedance matching perfect because I don't have a gamma match. It's not perfect, but it worked pretty well. And the amplifier plus the Yagi means that our signal was 10,000 times stronger than the regular transmitter. So we easily overwhelmed it and could pretty much attack the scoreboard from a sizable distance. And so I think that was handy to basically do that. And you could buy the amplifier on a website we found, and it's for SDR hacking projects. So
I'll follow up on that Yagi question. You could have done this attack with, I mean, if you only have a modulated frequency and it only flips really between two of them, you could have done it with a more simple antenna size to it from 100 feet. It just wouldn't have the strength.
Yeah, like we originally used like a dipole that we just kind of like set up to use for. I mean, we know the frequency, and it's easy to compute the length of the dipole that you need, and that really did work. But you didn't have the. We wanted to get our objective was to build a Yagi as long as we could. With the amplifier and the Yagi, so that we were just under the FCC federal limits for the amount of power you could deliver at that frequency. So because this is in the ISM band, and you have to keep things relatively quiet, like you can't radiate like many watts of power. So we were like, okay, what's the limit? And how many elements on the Yagi can I build before we're right at that limit? So that's why it's the certain number of elements long, is because I did that math, and I think we were close. I want to say that we were close for the radiated power that there, but
I think the important thing,
because I remember you building this. I remember you asking for help building this.
Oh yeah, I eventually found this. This brings you back a year there, but I basically found a website that showed you like where exactly like the precise measurements and the links that you need and how to build this. And like I said, it's not perfect, but it worked. So
what's the range on that sucker?
I never backed down the driveway long enough to figure it out, but we we walked. At one point, we walked like to the other side of your house, Maxwell. Like it was a sizable distance. Of course,
It
if
was
we
pretty
were
cool.
evil, like you wouldn't be worrying about the FCC limit, and you would just be making it as loud as you wanted to. But I'm pretty sure that this would work. Like I don't know, probably I want to say probably the range of like your car key fobs or garage door openers or something along those lines. I think it probably has approximately the same range. I don't know.
Would you be able to get it from across a basketball court?
Probably.
I think so.
Probably.
I think so,
Yeah.
especially if you were closer to the scoreboard than the actual controller. This would like it. You would never see a bad update.
Yeah, because the actual controller's got the same radiated power limitations as you if it's on the ISM band.
Right. Right.
But they're using an omnidirectional antenna as opposed to a focused antenna like the Yagi.
Yeah. Yeah, and I feel like something like this is stealthy enough where you could put it somewhere, like I said, like in a tree or something, and mess with it. And of course, in a real world, the display is different from the actual controller because I'm sure they're wired together. Like you have a wireless link, but then they're going to a big TV, so maybe the actual receiver is closer than you think it is. I don't know, but that was a fun thing.
Yeah. We should probably get back to the second.
We should probably get back to this. We can talk after. I don't want to go on too long. Why won't it let me jump through? Okay, there we go. It does it every time. Okay, here we go. Okay, so as mentioned before, one of the other projects we did was car key fob hacking. There's a 2019 vulnerability for Honda cars where the lock and unlock codes are very similar to each other in the air. And this was something that I pursued is transforming the lock code into the unlock code and being able to pwn basically your car. And to do that, we knew how to transmit for the Scoreboard project, but this involved receiving, which turned out to be a pretty sizable beast. But again, we turned to GNU Radio. So we use GNU Radio again to pull the bits out of the air from a signal that we've captured and identified. This is a little bit of a harder process than actual just transmitting, but the general steps are this. First, you have to use your good antenna to capture the signal. You isolate just the frequency that you want, the signal that you need, ignore everybody else in the spectrum. You kind of demodulate. And then you lock onto the bits, the ones and zeros that you need, and then you reverse the whitening or the line code or whatever you have to get the actual data that you need. This is kind of what we did in GNU Radio. So if you remember this from earlier, the first initial step is basically capturing this and saving to a file, and that way it's a lot easier, more reliable to work with. And that's basically what I did. So you can see them here in my directory. I have the raw file that I captured, and then I do a little bit of cleanup on the next one, just so it's easier to work with. And then this is a much simplified flow graph for GNU Radio for receiving. And again, it's a little complicated, but we'll take it step by step. So the recording is wide. When you capture something with a Hacker F1 with a software-defined radio, you're capturing many megahertz of bandwidth, and your car key fob, your scoreboard, whatever you're dealing with is really, really tiny. And so your first objective is to simply dial it down to just what you want. So the block that we use here, and again, it's based on Python, is the frequency translating FIR filter. And it has a very good diagram on how this works. So say you capture something, it does a couple of steps in one block. So you may remember we had a hardware issue in the Hacker F1. We're recording slightly offset to avoid some issues with that. And so we do that translation, shifting this orange block that we care about slightly over. Then we do basically, we run it through a filter to remove everything else that's out there. So for example, we just want the Honda car key signal. We don't want like TV broadcast, FM radio. We just want that. And then we decimate the recording because we don't need so thorough of a recording with so many samples for just a very a small and slower signal like that. So that's the first sequence of the blocks in this flow graph. Our second step is basically demodulating. So we have a squelch, and that basically is just going to be eliminating all the quiet noise, because the signal we're dealing with is going to be loud. We're in close proximity, so we can kind of cull any of the quiet signals. And then the next step is the demodulating step. This does some interesting mathematics with complex numbers, but basically it just prints a positive number if the upper frequency is loud, and a negative number if the lower frequency is loud, and a 0 if nothing at all. So this is the key for frequency shift keying, where you're jumping between these two different frequencies. From there, we just basically do some cleanup where we're converting these to ones or zeros, and then we feed it into a graph. And when I build these graphs, this is kind of what it looks like. So we first take our raw feed from the Hacker F1 we've captured from the air. You see these two little spikes that show that we're jumping between there. When I press my Honda car keys, there are 3 packets, 3 bursts that are being transmitted. They look kind of like this. And as you can see, I've isolated them pretty well to just those frequencies that they're on. And then I demodulate it. And again, as you saw in an earlier slide, you see these, high frequency, low frequency, and there's this alternating jump back and forth. And then we basically just convert these to just the ones and zeros, creating this sort of chain that we have here to work with. This is essentially works pretty well. That's basically it. This is what the Python looks like. It's a little bit longer, but it's still kind of structured the same way. You've got variables that you're kind of defining. You've got the frequency that it's operating at 313.85 megahertz, and the speed of the baud rates. Then you've got the blocks that you've defined, and then you're connecting those blocks together into the flow graph that I talked about. Again, it's just Python under the hood. You can set this all up yourself in Python with the GNU Radio library, but I like using the GNU Radio companion just to make things easier. And at the bottom of the GNU Radio, bottom of the Python file are these hooks. We talked about these earlier as the same way that you would use to hook into this. Is there a write-up of this for GNU Radio or for like receiving frequency shift keying? Feel free to write this into my project. I gave a presentation. I don't have a write-up yet. No, I gave a presentation on it, but I have to do some more cleanup on my code before I feel comfortable kind of like pushing it out and making it professional. There was not a whole lot of good results even on Stack Overflow as to how to do this, so a lot of it I kind of was figuring out myself, but yeah. So this kind of works. I kind of built these end graphs, but you do have some pretty key problems. First, the bits are way oversampled, so each 1 or 0 is like way expanded out. You have many ones, many zeros, many ones, many zeros, instead of just the raw bits that you need. And also you don't know when the raw signal starts and stops. And the solution to both problems here is once again Python. So the clock synchronization is the first step. If you have an oversampling of the ones and zeros, to lock onto those, you do a step called clock synchronization. This turned out to be one of the hardest, complex, and time-consuming parts of this entire project. I really started to dislike this as I kept going and hammering my head against the wall because I didn't understand how this truly operates. This is not my background or my field, but it's the key part of the entire procedure. So in the end, I kind of cheated. I spun up some sliders in a GUI and I slid the numbers around until they started working. So basically the symbol sync block locks onto the middle of these ones or zeros sequence and sort of extracts them to just print out the 1 0 1 0 pattern. So that's the That's the key part to that. And it works pretty well like this. So in my modified version of the flow graph, I start with that demodulated procedure. I do a little low pass filter to remove these little spikes, clean it up quite a bit, and then run that block. And the red line here is the error rate. Now, as you can see, it locks on pretty well. Now you can see once again that for consecutive ones and zeros, there's quite a bit of error, which is why you can't really continue the same bit long enough, or you'll have that completely fall off and it'll lose that lock. So, but in this signal, it's whitened and cleaned up, and it doesn't have that problem. So it locks on pretty well, and it stays locked, and we print out the ones and zeros exactly as we expected. We get the bits that we need for this project. Yeah, this has Manchester encoding, so it's similar to whitening. It's slightly different. And again, it's Python. So here we have the low pass filter that does that little cleanup, gets the waves looking like I want. Then we run the frequency translating FIR filter. You pass in these parameters, and then you have the symbol sync block that you're passing in the Mueller and Muller algorithm and the particular parameters to the algorithm that you need to basically run through that lock. And then the rest of the flow graph, and you connect all these blocks together, as I've talked about before, and then it works pretty well for you in Python. So the second problem that we're solving here is identifying the start and stop of the signal. Now, it's no coincidence that this 11110010 pattern is here. That's because this is a Barker code. This is something that I realized when I was Googling around, and I realized this is not a coincidence. This is not by random. This is because when these two are when you slide a known signal with what you've captured, at a certain point they line up perfectly, and you get an extremely strong correlation that's much higher than when you're not perfectly aligned. So this can tell you when exactly the signal starts, and that's what I utilized in Python for this step. There's some blocks in Python that let you do that correlation, and as expected, right at the beginning, it peaks right at that spot because of that Barker code and the preamble that we have here. The preamble is critical for the clock synchronization, and the Barker code at the beginning tells us where it starts. So then we know how to go from there. And then to basically start and stop the signal, I wrote some custom Python in GNU Radio to open and close, and I called this block a preamble gate. This is probably not the most professional way of solving this problem, but that's the method that seemed to work pretty decently for me. So I basically queued all of the samples and all the correlations into a queue, and then once the correlation is above a certain threshold at the beginning of that signal, then I start feeding out of the queue, and then the gate closes after a certain length. So it sort of opens when it correlates, and then closes after a certain amount of time, and it's all basically in Python. And it looks like this. So this is the custom Python you can write for GNU Radio. And again, it's all Python, so it all hooks together pretty smoothly. I pass in the variables that I need. And then just to kind of quickly sum this up, you basically shove a bunch of stuff into the queues, and then you sort of extract them from the queues and return them into the rest of the flow graph based on certain conditions. So this is kind of something that I kind of organized and wrote up in the Python. In the end, you kind of build a receiver like this. You combine all these steps together with the demodulating, or the signal isolation, the demodulating, the correlation, the preamble gate, and then the clock synchronization. And now I can extract the ones and zeros that are coming through the air. After I do this in GNU Radio, I then apply the CVE, and I use the translating steps that we talked about earlier to actually deliver it out, and then that works. And so I'll show you now that procedure. Share screen of
Jesse, please tell me what works. What works?
Oh, the GNU Radio and the Python, they work. Is that? Yeah.
No, like you open the car, right?
Oh yeah, absolutely. So this is me basically pressing the lock button, and then I do all of these things and transmit the code, and it unlocks. So basically, I can essentially break into my own car, and that's the key to. Here we go. Yeah. So yeah, the receiving of the frequency shift keying, the applying of the exploit, and then transmitting allow me to kind of do these real-time attacks thanks to the Python. Then back to you. Yeah,
I am muted.
Yeah.
Round of applause to Jesse. That was really awesome. I watched him go through a lot of that stuff, and that was really crazy. So good job to Jesse for getting that working. That was pretty awesome. Yeah, that's our talk. In conclusion, SDR is amazing, but GNU Radio is amazing, and so is Python. So a lot of really cool stuff. I feel like we got to talk about and I'm happy to share. Signals are hard and complicated, but I think with enough effort, enough understanding, enough reading, this tool is usable, and you can do some really cool stuff like we showed today. Yeah, does anybody have any questions?
So just because I'm old and slow, you were able to take a lock code and turn that into an unlock code.
Yeah. So the key
You
to
didn't capture another unlock code.
No. I captured the the vulnerability. Not a problem. I skimmed through it pretty fast. It's okay. In Honda cars, they don't have rolling codes. So every single time you press the lock button, it's the same sequence. At least on the old, I have a 2008 car, so it's not, maybe it's not updated, but at least in a lot of the models, your lock code is the same every single time you press that button. It's the same wireless signal every time. And when you press the lock button and the unlock button, they differ from each other by only about 4 or 5 bits. So at certain positions, for the lock code, it's a 1, and for the unlock code, it's a 0. So what you can do is you can capture the lock code, run all the GNU Radio stuff to get like the actual bits. You flip those bits, and now you have the unlock code, and then you transmit the unlock code, and you've unlocked the car. So if I was evil, what I would do is I would set up GNU Radio, Python, and I would have it running on a Raspberry Pi, and I would hide it away in a parking lot, various sneaky spots in a tree or something in the bushes, I don't know. And when you go into the grocery store, everybody locks their car, but now you've got the lock code, and you can just flip the bits and send the unlock code, and you can unlock your stuff. I've seen also people do signal attacks to attack gas pumps, because gas pumps go into have a mode for the auditors, the people to check them for calibrating the pump accuracy, and so that you can wirelessly convert some of the pumps into this maintenance mode where it pumps gas without going through the payment system. And so someone figured, I've never actually seen a talk about this, but I've seen actual bad guys do this. There's a video of somebody that stole like $500 in gas. It's on YouTube somewhere. I saw it a couple months ago, and takes out a wireless device and does this, and it does these kind of attacks. Of course, I mean, I'm in cybersecurity, so I'm looking at all these kind of things, but you can use GNU Radio and the Python for all sorts of quite useful kinds of projects, and so it's not just for attacking and breaking stuff. Yeah, the unoriginal rice patty is the vulnerability Maxwell linked in chat. So yeah, it's some interesting stuff.
Yeah, any other questions on what Jesse just talked about, or about what we talked about as a whole, or anything else?
I'll throw a couple at you guys, just kind of in closing, or if someone else has any questions. Max, you mentioned you found one of the tools, I forget which one it was, listening to a podcast. Going off that, maybe you guys could share a couple resources that you go to for, learning more about this kind of stuff. Podcasts you listen to, YouTube channels, blogs, maybe just one or two of your favorites.
Yeah, it's a good question. So I feel like a lot of the tools I use are like reverse engineering tools. And there's a podcast called Unnamed Reverse Engineering Podcast. Again, literally Unnamed Reverse Engineering Podcast is the name of it. And that's why I found a lot of these tools, actually.
Awesome. Thank you. Jesse, anything to add?
Are you asking me? Yeah, I would say rtosdr.com is for me one of the greater blogs in terms of people that do projects like all sorts of interesting projects with a very, very cheap hardware. So it becomes very attractive from like a hobbyist of like, oh yeah, I could do this too. And so a lot of that stuff is interesting, but there's some of the stuff pops up in the NetSec subreddit. But I haven't heard any podcasts that I listen to that are focused on the. Oh yeah, rtosdr.com. Thank you. Yeah, with a dash.
Awesome. Thank you guys. Where can people find out more? I think Max dropped a link to his blog if they want to follow along with, list your blog, says RF Noob. Yeah, Twitter handles, whatever.
Yeah, Maximo's got a good blog. I don't have one, but there you go. But basically we've been publishing these on the internet about the Scoreboard project. We've also released the source code on the source code for the API and the GNU Radio and everything that we needed to basically create and run our own virtual controller for this. We've been very careful not to release like the vendor name and the particular product page on this. We've censored it out from everything because it really doesn't matter. It's about the technique. It's about the process that we used to kind of figure it out, because you can take a lot of this for many other things. So
the code for the transmitter is on our company GitHub right now, though.
Yep.
And it's linked in the third blog post, I believe. And I just linked my GitHub as well, and it probably showed my contributions. And you did disclose this to the Scoreboard maker, right?
Yeah,
we
did to the company, and they ignored us completely. We basically we spent, how many days was that, Max? Well, we spent like 4 days carefully crafting the right diplomacy on like, okay, we're following all the legal processes, we're following all the procedures, and we were like, okay, this looks professional. We linked to our like company page to show that we're actually following our own defined process for public disclosing public vulnerabilities, and we got no response. And it was like, okay, well, that's maybe they were busy, maybe they didn't care, maybe they thought that our message was spam or aggressive. You have to be careful about this stuff because sometimes people can get very, very angry when you try to disclose issues. I would like to, I don't know that they know that we reverse engineered all of their stuff to the degree that we did. Maybe they might get angry about that, but I hope not.
I mean, at the end of the day, the cool stuff is the technical stuff we went through. I don't feel like it's like that. Like, I don't think the tool's that that use it, or that many people would use the tool. It's like the process and understanding and the reverse engineering, the GNU Radio stuff. That's all cool. Yeah, that's good. Yeah. And any other questions from people? Sean, you did not graduate from Centralia High School. There is no way.
Yeah, I did. I actually didn't go to the school my senior year because I was doing the running start or whatever at Centralia.
Oh my gosh, that's so funny.
Yeah, 99 Centralia High School.
Small world, man. That's awesome.
Cool. Max, Jesse, thank you guys a lot. Really appreciate you guys hopping up on relatively short notice to give this talk.
Very cool.
Yeah, super interesting. I'm looking forward to reading the blogs as well. Haven't done that yet. I'll throw out one final plug. We don't have a speaker for next month or the next meetup. Glad you all could be here. If anyone wants to speak, Maxwell did mention that I was even willing to pay first-time speakers. I think there's more info on the Spokane Python website. You can check it out there, /speak. There's even a little form and stuff, or you can just email me directly, call me, smoke signal. Anyway, any way to get a hold of me, and we'll figure something out.
When's the next meetup then?
Well, TBD. We'll see if we can get a speaker or not. I guess the long and short of it is for several months in a row, I was speaking, and I just don't think I'm that interesting. So we'll see if we can wrangle someone up to speak next month. But if not, we'll see if there's a meetup or not. But typically the third Tuesday of every month. So maybe like November 15th if I find someone. If not, and I find something interesting to talk about, maybe I'll host, but we'll see.
Cool. Well, thanks for having us then. I'm glad we got to share this weird piece of knowledge, and hopefully somebody gets some out of it.
Yeah, absolutely.
Great job.
Thanks,
Yeah, thanks, guys.
Thanks, guys.
Yeah, Sean. Sorry. to
Maybe
answer
stop recording now.
Gordon, I'll let it run on our end in case anyone has questions that it's here in person, but
Sure.